A two-area interconnected power system have been designed, which consist of uh, two power system area. Upper portion indicate power system 1, lower portion indicate power system 2, connected tie line, I mean transmission line, with different power system component. So here there is no controller. We can see there is no controller here, and the response of the system for without controller, we can see in far system area 1 indicate by red waveform, and far system area 2 indicate by blue waveform. So here we are not getting desired frequency deviation without controller. To get desired frequency deviation, we need introduce controller in the system to the system, and the frequency must be kept constant at 50 Hz, and the deviation should not be exceed plus minus 0.5. So here we have introduced a fuzzy logic controller in the system into the system, and LQR controller to the system. So we are going to compare the response of system in area 1 and between fuzzy logic controller and linear quadratic regulator controller. So for load 1 power unit, we can see in area 1 the response of fuzzy logic controller is presented with red waveform. The response of LQR, I mean linear quadratic regulator, is presented with blue waveform. So we can see for 1 power unit load, the frequency deviation remain within desired value, and LQR controller exhibit better performance over fuzzy logic controller in term of compensative frequency deviation and overshoot, and fuzzy logic controller exhibit better performance in term of SCS error compensating. And in area 2, we can see the LQR controller shows better performance than fuzzy logic controller in compensative frequency deviation and overshoot control. And we are going to change the load. We are taking 2 power unit in both controller. For here we are going to analyze in area 1, and it shows the LQR controller represent better performance than fuzzy logic controller in terms of frequency deviation and overshoot compensation for load change for under dynamic response, I mean 2 power unit load. And we can see in area 2 also LQR controller exhibit better performance over fuzzy in term of compensative frequency distribution and combating overshoot, but in term of stage to error reducing fuzzy exhibit better performance. So we are going to change the load. We are taking 4.5 pu load in both controller to analyze the response. So we are going to get the first area. In first area, we can see for 4.5 pu load LQR controller, the response of LQR controller shows superior performance than about the fuzzy logic controller in terms of frequency deviation and the overshoot. And in area 2 also, the response of LQR controller remain within desired value, but fuzzy logic controller response distort from the desired value. So here also LQR controller exhibit better performance in terms of compensative frequency deviation and overshoot. So in we can see for we can see the for load 5, we can see for loads we are changing load 5. We are taking power unit 5 power unit in both for both controller. We can see in area 1 and LQR controller also exhibit better performance than fuzzy logic controller, and area 2 also we can see LQR controller shows better performance over fuzzy logic controller in terms of reducing overshoot and frequency deviation. But here LQR output response also distort from the optimum value. I mean it cannot maintain a frequency deviation within plus minus 0.5. It goes beyond the limit, and also we can see fuzzy logic controller represent a frequency division that is far beyond far below than the desired value, 0 plus minus 0.5. So here we can say for under dynamic condition, LQR controller exhibit better performance over the fuzzy logic controller in terms of reducing frequency deviation, compensating overshoot, and fuzzy logic controller represent better performance over LQR in terms of reducing SCH to error. Thank you all.